Hey guys, this is Andre from Wealth Neighbor. Hope you are all doing well. In this video, we will play around with a formula that gives us the future value of a current amount considering compound. We will also see a new formula based on the previous one that also considers periodic payments or periodic investments, because sometimes it's more realistic to consider that we are not going to invest the whole amount once and wait for a long time. We will keep investing through constant time intervals. After I show you guys these formulas and some hypotheses that the formulas consider, we'll analyze an investing scenario and use these formulas to see how much we have to invest and how long and at which interest rate to reach our financial goals. And in order to calculate all these numbers, we'll see how to solve nonlinear equations in Excel. I will show you guys 4 different methods to solve these nonlinear equations, including a tool in Excel called Solver. So look forward to it, guys. I would like you to take a minute and read this disclaimer, and if you agree with all the terms and conditions, let's start this video. First, we'll talk about the formula that calculates the future value with compound interest. Then I will show you a slightly different formula that considers periodic deposits and compound interest. We'll see all the assumptions and hypotheses these formulas take, and then we'll analyze a retirement scenario and see how we can solve a nonlinear equation in Excel in 4 different ways. So guys, if you remember from one of our previous videos, this is the future value formula with compound interest. So this formula tells us that the future value of a current investment equals the amount invested right now times 1 plus the return rate of our investments divided by the number of periods that return rate is compounded throughout the year, to the power of the amount of years we keep this investment times the number the interest is compounded per year. And after some algebraic manipulation, we can get from this formula to this new formula that considers periodic deposits. This formula says that the future value of a current investment equals the amount deposited every period times 1 plus the return rate of the period to the power of the number of periods minus 1, and all that divided by the return rate of the period. We can say that this formula is more realistic than the previous one because we usually invest money on a regular basis instead of investing the whole amount only once and then waiting for a long period of time until we get the results we are expecting. So we usually be able to invest a little bit every month, for example, or maybe every 4 months, and this will make our investment grow faster. The 2 previous formulas I showed you guys are not real life formulas because they take some assumptions that makes the calculations easier. So let's see. We can either consider daily, monthly, or yearly compounding as long as all the units are compatible. So for example, if I use a monthly return rate, I have to make sure the exponent of the 1 plus return rate term is also in months. I have to make sure all the units are in the same time basis. Both formulas also assume constant return rates, or R will not change throughout time, which is kind of unrealistic because it's very hard to guarantee a return rate, especially for long periods of time, but this is one of the assumptions we are taking. The second formula considers constant periodic deposits. So I will deposit the same amount every period. For example, $100 every month or $500 every 6 months and so on. The deposited amount will not change throughout time. The formulas also assume that the interest paid on our principal will be compounded at the same return rate from the initial investment. And in the second formula, the deposits are made at the beginning of each period and at the same return rate as of the initial investment. All those return rate considerations are a little bit strong because it's hard to guarantee we'll be able to get the same return rate as we got when we started investing our money. But again, this is another consideration this formula is making. So based on these assumptions, we can see that the value we calculate from our formulas are just estimates based on all those assumptions we are taking. Now, in order to use those formulas and calculate some values, let's get to the scenario analysis. So say I want to retire 30 years from now. My goal is to have $1 million in my retirement account, and I think 8% average yearly return rate is reasonable for the amount of risk I'm willing to take. Based on this scenario, how much do I need today to make my retirement goal come true? Or how much do I need to deposit every month starting today to make this retirement dream come true? So in order to calculate these amounts, we use the future value formula. And here we have some methods to solve that nonlinear equation in Excel. The first one is not really limited to Excel. It's called algebraic manipulation, or the expression isolating x might sound more familiar to you. This means that we'll isolate the variable we want in the equation and then substitute all of the other variables by their numerical values and evaluate the variable we want. Algebraic manipulation leads to what is called an analytical solution, which is a 100% correct solution. But sometimes the equation we have to solve is so complex that it's really time consuming or even impossible to solve it analytically or by algebraic manipulation. So mathematicians have developed other methods to solve these nonlinear equations. And the second group of solution leads to what is called a numerical solution that is not 100% accurate. So numerical solutions are usually calculated by algorithms, be it a dumb algorithm like guessing or evaluating the function for different values, or automated and smart numerical solutions, such as the computational algorithms that the solver tool in Excel uses to solve nonlinear equations. Before I explain in more detail how solver works, we will try to solve this problem we have at hand using both algebraic manipulation and evaluating the equation for different values or guessing. So let's move to Excel a little bit. In this spreadsheet, I have all the information I need to start calculating the present value or the periodic deposit amount I need to reach my financial goal based on the scenario defined earlier. So my future value is $1 million. This is my goal. The time I have to reach this goal is 30 years because I want to retire in 30 years from now. My return rate is 8% because I think 8% is a reasonable return rate based on the risk I'm willing to take. And finally, n equals 12 because here we'll consider that interest is compounded by month, and it will also make it easier for us to calculate the periodic values based on a monthly basis. So for now, let's try the first method, or solving this equation by algebraic manipulation. I use the cells here to save the values we get using the different methods, and so that we can compare them later and see how different they are. Okay, so using algebraic manipulation, what I want is the present value, and I already have all the other variables in the formula. Luckily for me, it's very easy to isolate PV in this formula here. All I have to do is divide FV by this whole term here, 1 plus R divided by N to the power of N plus N to the power of N times. Okay, so let's start to calculate this present value using algebraic manipulation. So, present value equals future value divided by, here guys, be very careful where you open and close this parenthesis, because if you're not paying attention, we might end up with some error and we have to fix it later. So, future value divided by 1 plus R divided by N to the power of T times N. And using the first method, algebraic manipulation, we get to a total of $91,443.4. This is how much we have to invest today to get $1 million 30 years from now at 8% return rate, compounded 12 times a year. These are called PV, and this will be the PMT. So let's see how much it is considering periodic investments. So I will do the same thing, algebraic manipulation. PMT equals future value times So how much should monthly deposits be? I have to deposit a total of $670.98 every month for 30 years to get $1 million 30 years from now at 8% return rate, considering that interest is compounded 12 times a month. So this is the first method, algebraic manipulation. We get the exact analytical results, but we were only able to solve this by this method because these equations are not very complex and are quite easy for PV and PMT. But what would happen if we had to solve this for R or T? For example, T is in the exponential term, and we are taking a power of R here. So this makes things much more complex. The numerical methods are here to help us in this situation. In the first situation, we actually don't need any numerical method because we are able to get the analytical result easily. But I will show you guys how to use the numerical methods here, and then when the problem gets more complex and more difficult, we will be able to use analytical methods without any trouble. So the second method is the extensive computation of the formula. So here I will have FV and PV. So FV equals PV times 1 plus R divided by N to the power of T times N. And there you go, I have 0 here because I have 0 here, my PV is 0. And now I want to evaluate this formula for different values of PV and see which value of PV gets the closer to my FV goal as possible. So here I already know that PV will be 91,442. So I will evaluate this formula in $10,000 intervals. So here I have 10,000. In the next cell, 20, 30, 40, 50, 60, 70, 80, 90, all the way to 120,000, because let's pretend I don't know what's the real result. And I will also drag down this formula. Observe that I got this error dragging down the formula. You guys should already know why this happened. And the reason why is that I forgot to lock all these references here. So let's fix this error. And now drag the formula again. And there you go, guys. This is the future value for different present values, considering all these other variables here. So t equals 30, r equals 8%, and n equals 12. And from this table, I can see that the amounts I'm looking for, which is 1 million, is somewhere between 90,000 and $100,000 invested. And I would just estimate here something like 92,000. I could redo this computation. For example, here I already know that it's some value between 90,000 and 100,000. So I start from 900 and use smaller increments. For example, instead of 10,000, I will just use 1,000 and evaluate the formula again all the way to 100,000. So I would get closer and closer to the real amount, the amount that gets me $1 million in the future. But I will not do that here, guys. You already got the idea, right? And we can do the same thing for PMT to calculate PMT. But the main differences are, instead of PV, we can create an additional column here called PMT. And we have to use this different model here, the second equation, to calculate the future values. Now the third method and the second numerical solution I mentioned earlier is using the Excel tool called Solver, which is this button here. But before showing how this tool actually works, we will go back to PowerPoint and explain it a little bit better. Okay guys, now we already use algebraic manipulation and extensive evaluation at different values to solve our scenario, and our third method will be using Excel tool called Solver. So what exactly is Solver? So Solver, guys, is an optimization tool. It will try to calculate the value of a target cell, either minimize, maximize it, or make it reach some other value we impose by changing the values of other cells while making sure they are within certain constraints we impose. Try to think of it as an automated guessing solution. Not only automated, but also smart, because Solver is based on different search algorithms that will try to bring us to the solution of the problem we're trying to solve within the shortest amount of time. The algorithm will try to be as concise as possible. When we are dealing with optimization problems, we always have to deal with the difference between observations and calculations. The particular scenario we are trying to solve does not have any observation because we don't have real data from anywhere. We are just trying to solve an equation. But most of the time, we will have a set of observations, and we will try to use an optimization routine to fit this set of observations to a model. A model is an equation or a set of equations that can closely represent our observations. So let me give you guys an example here just to make things easier. Remember when we were trying to fit the daily balance in my Nubank account by a second order polynomial? In this case, the daily balances are the observations and the model is the second order polynomial. The second order polynomial is an equation, right? It has dependent variables, independent variables, and parameters. So in the daily balance fitting case, the dependent variable is our estimate on the daily balance. The independent variable is time, and the parameters of our model are the coefficients of this polynomial. So our model is estimate of daily balance equals coefficient 1 times the day squared plus second coefficient or second parameter times day at the first power plus a third parameter. Now, optimization problems are usually defined by this set of equations. So we usually want to minimize an equation or a set of equations that is a function of an independent variable, parameters, and what we call here the decision variables of the optimization problems. The decision variables are the actual variables that the algorithm will change in order to reach the optimization goal, subject to bounds on the decision variables and some additional relationships and equations. So this is a generic representation of an optimization problem. But our scenario for now is much more simpler than this. So the target of an optimization problem is to minimize a function. I wrote here that the target is to minimize the sum of square errors between observations and model evaluations. So this is the target we use in our model. The constraints affect the independent variables of the problem and also the parameters. So for example, when we try to solve the future value formula for time, we might want to impose a condition. We want our answer to be an integer or an integer number of years. We don't want fractional values. So this would be a constraint to the optimization problem. And finally, the decision variables are the variables that the algorithm will try to calculate. For example, in the previous case, when we solved the future value formula for a present value, because we already had the future value and all of the other variables, the decision variable in that case is the present value, or the PMT, the periodic deposit amount. And now, how to use solver in Excel. I will give you guys some general guidelines. They might differ based on the complexity of our problem, but basically this is what we have to do. First, define a model or define your equation. Define what is going to represent your set of observations. Second, define the decision variables of your model and bounds, if any. Third, define a target or what the optimization problem will try to solve. Fourth, define the optimization problem's constraints, if any. Fifth, start the solver tool, but we will keep all the settings as default for now, because this is not an optimization course. This stuff is very complex and takes a lot of time to learn. We are just using the most basic functions of solver here, guys. And finally, always remember to check your answer and see if it makes sense. Remember that every optimization algorithm is just a tool. It will perform the calculations for you. It will make your life easier, but you need to know how to use this tool and you need to know how to interpret the results. I believe this is the most important thing I have to say in this video, guys. So now that we are more familiar with solver, let's see how it works in practice.